Now, let's have a read of today's fact, which is about Hans Lippershey. This is brought to us, I believe, by David, but I might be wrong. I might have got that wrong. Hans Lippershey was an inventor born in Wessel, Germany in 1570. He was a spectacle maker, spectacle being glasses, for the United Netherlands, traditionally credited with inventing the telescope in 1608. He applied to the States General of the Netherlands with a 30-year contract that allowed him only to invent his own ideas for the state. In exchange, he was for the contract, he didn't sell telescopes to foreign kings. So it's like, hey, cool, I can make whatever I want for 30 years, which is a pretty good job as an inventor, but I can't sell my inventions to people outside of Germany. So many people knew the telescope quite thoroughly. So the state of general ruled out that there would be no patent given to them except Hans Lippershey. So essentially, he was the only one that had a patent. A patent, by the way, of course, is proof that this is my idea. The State Journal had given Hans Lippershey $4.19 for a telescope that was modified into binoculars. He sold these telescopes to Henry IV. France and others before the end of 1608. Hans Lippershey, however, assumed to have stolen the idea of the telescope from the eyeglass maker Zacharias Janssen. Since Hans Lippershey was allowed to work with others, in the end he gets credited for all the work combined. That's an interesting take. I'm going to give that to this person, because usually the idea is Hans Lippershey had his theory of the telescope stolen by Galileo. And so to say that Hans Lippershey was the one that stole it, I have to admit, though, I will point out that leaving hyperlinks inside of the text that you send to me kind of suggests that you've stolen that piece of text. And I think I looked through it, and I think some of this has been stolen from different places, but it has been reworded slightly. So I'm a bit hesitant to say how credible this is. And there's no sources cited, so I have no way to know. But yeah, it's an interesting point. We'll talk about, firstly, if you're going to reword something, if you're going to steal something from the internet, guys, or reword something from the internet, remove hyperlinks so that your teacher can't obviously tell that this was taken from the internet. But I will mention as well, though, it's an interesting take on it. I think the thing with telescopes is that telescopes are ultimately just two pieces of glass in a tube. So the thing about telescopes is that a lot of people came up with the idea, and it's kind of hard to say who came up with the idea first, given it's a pretty interesting little design. And I reckon that a lot of people were making them, and I think a lot of people could be credited as the inventor. But I think it's hard to know who was the actual inventor of the telescope. But yeah, usually people say, oh, Galileo invented the first telescope. He didn't. He just was he just perfected the telescope. And he also gave his telescope to a famous Italian lord, who then, of course, told everyone about it. Galileo did discover the moons of Jupiter, though, so that's a bit of something, but yeah. Lesson 17, projectile motion. So the idea of today's lesson, we're going to learn about projectile motion. Now, projectile motion is one of my favorite topics to teach, but to be honest with you guys, and it's true, it's one of the hardest topics to learn. The reason that I love, and I always put the projectile motion at the very end, is it's almost like, in my opinion, a challenge topic. What we do in projectile motion is that we take everything that you've learned so far and we mush it together into one large idea. And I think it's a kind of interesting thing. We take vectors, we take gravity and our understanding of Newton's laws. We also we take a bit of kinematics. We take a lot of kinematics, actually. And we sort of bring all of these things together. And that's why I like this topic to end on, because at the end, it's almost like a little bit of a revision. It's like you need to have a good understanding. And yeah, sure, there are a couple of new ideas here, but ultimately projectile motion doesn't actually have anything new in it. It's just the old theories that are all getting applied at once. There is one key point that you do need to understand, but once you understand that, I feel like it's a pretty easy topic. Well, no, it's not a pretty easy topic, I'm not gonna lie, it's complicated, but there's only one new idea. The rest of them are just new combinations of old ideas. It's kind of like, in this way, it's a little bit like art. When you start off doing art, you only learn how to do one type of art, which might be how to draw, but then you might learn how to paint. But then it's really interesting if you combine drawing with painting together. Movie making is the same. You might learn how to use one program, you might learn how to use another program, but you put them together, you get something more complex. And that's what's going on here with projectile motion. Before we do projectile motion, before we start, by the way, projectile motion is pretty much a week-long activity. We're not going to get through all of it today. We're going to be working on it tomorrow, maybe even Thursday as well. But then I want to give you guys some time to work on it, work on some of the questions. And again, this is also the most complex section. If you guys get to the end of this and you're like, whoa, I have no idea, then don't be too shocked, because yeah, it's also good because it gives you guys a bit of a, for those of you that are doing, advanced maths and looking at projectile, looking at quadratics, then this just should give you another way to think about the quadratic formula. But yeah, that's going to come up as we go. Let's go backwards for a second to talk about just what we talked about at the end of last week. At the end of last week, we were looking at these net force diagrams, and that was because we just finished talking about Newton's third law. So we looked at net force diagrams. Net force, force diagrams. Remember, action-reaction pairs are the same size. So what we did was we looked at, for like apples in space and apples on the ground, what are the forces acting on them, and what are their action-reaction pairs. We looked at stuff like bookcases, and then after bookcases, we started to look at just what are the forces acting on this bicyclist. We don't care about all the action-reaction pairs, but just what are the net forces. And then we finished up by talking about this apple falling towards the ground. What is the overall force on this apple? What are the forces acting on the apple? And then we started to work on motion 5. So let's jump into now working on projectile motion. The first thing we should state is, what is projectile motion? Projectile motion. Projectile motion is the motion of objects through the air in 2 dimensions. And that's what makes this topic a bit more challenging. What we've been doing so far is we've been dealing with just 1 dimension. You might not be aware of that, but we have been. We've been talking about, when we talk about like a car coming to a stop, we're just talking about a car going forwards and backwards and coming to a stop. We're not talking about how it changes its up and down movement. Even if we talk about, if you look at all the questions we've done so far, even when it says something like, oh, this object was thrown upwards, it says upwards. It doesn't say up and to the right, it just says upwards. But now what I want to do as a final thing, as a big extension to this, is I want to explore projectile motion, because it's a 2-dimensional motion. And this is also really important. Ultimately, if you can't imagine the world in 2 dimensions, you're going to be in a bit of a pickle. You really need to measure it in 3 dimensions, but we need to start breaking away from just dealing in 1 dimension. Now, the horizontal velocity is dependent on how quickly it is thrown horizontally. This is something that I'm going to talk about a lot. But it's actually, and I personally have seen lots of experiments done on this. I've looked at it myself, but it's still a fact that I'm always like, wow, that's so weird. Ultimately, if you throw something to the right at a speed of 10 meters per second off a cliff, it will fall at 10, pardon me, sorry for yawning, it'll keep going to the right at 10 meters per second forever. It doesn't stop, it just keeps going to the right at that speed. It's interesting that this is completely different from the vertical velocity. The vertical velocity or speed, how far it goes up and down, is dependent on the initial vertical velocity and gravity. So whilst if you drop something off a tower, it will get faster and faster and faster because of gravity. Gravity doesn't affect how far across it'll go if you throw it. So it's a bit of an interesting idea. And we're going to explore what these two ideas mean. What do these two ideas mean? Horizontal, by the way, is left to right, vertical is up to down. We're going to explore what these ideas mean, how they impact projectile motion, and then we're just going to see, it's like, okay, how can we estimate some things? If I want to make sure that I throw a ball 20 meters, how high upwards should I throw it? How hard upwards should I throw it? That's what we're going to be calculating. I'm going to give you guys a minute to copy this down, 30 seconds to copy this down. I'm going to change the slide. If you need more time, please let me know. But yeah, I'll give you guys about 30 seconds from now. By the way, in the picture on the left, you actually have evidence of 3 different ways you can look at projectile motion. The first is just dropping an object. The second is throwing an object up, and then that object comes back down. And that one's a bit more interesting because that's got 2. You can think about this one as having 2 parts, the up part and the down part. And the same for this one. The difference between this first one and the second one is this second one that she's not just throwing it up, or the boy's not just throwing it up, he's throwing it up and to the right. So therefore, it's going to slowly but surely keep going to the right. You don't need to draw the pictures. I just wanted to put those pictures in something to add to the slide. So let's break this down then, okay? We're going to look at horizontal velocity and vertical velocity. How can we think about this a bit better? Actually, let's look at these horizontal vertical velocities. Now, you don't have to copy this picture down, but this is actually an example of, yeah, the same sort of thing. Is like shooting a cannon off a cliff. Now let's look at the cannonball as it goes off the cliff. I'm going to change to a different color. I'm going to look at in blue. Let's look at the horizontal velocity. It starts going to the right at 20 meters per second, 20 meters per second, 20 meters per second, 20 meters. It's going to the right at a constant 20 meters per second. No matter what, that speed is only dependent on how quickly it is shot out of the cannon. So horizontally, it won't matter if you're right in front of the cannon or you're really far away from the cannon. You're still going to experience 20 meters per second. The vertical speed, though, well, that is something a bit more interesting. The vertical speed starts off at, well, 0, then 10 meters per second down, then 20 meters per second down. In fact, it's getting faster and faster and faster. We call this an acceleration, because that's what it is. There's a change in speed, and we say that acceleration is caused by the force of gravity. This does not occur left to right. It doesn't get faster and faster or slower and slower left to right. And before I get someone smart ass saying, well, what about air resistance? We're going to ignore air resistance. Air resistance would play a role, but we're not going to deal with it. We're just going to like say, well, this is how an example. Here's a different picture. I like this picture too. It's an animated GIF. There's a lot that you can actually extract from just such a simple picture. So this is someone maybe throwing a ball, maybe shooting a ball off a cliff. And what we can see is we can see the path that it makes. Now, if you are if you're again, like a advanced math student, but even if you're not, if you're just an intermediate, that's okay. But you should be able to maybe see this shape here. That's a parabola. If you look at this, this is a parabola. And it's making this parabolic shape. So, and that's exactly, that parabolic shape is going to be, you'll be able to see why it makes this parabolic shape when we start to talk about the equations. And the equations, just the kinematic ones, we've already done, but it's just an interesting way. Now let's look at something else. Let's look at the horizontal speed. It's 60, 60, 60, 60, 60, 60, 60, 60, 60. The horizontal speed is constant. It is a constant 60. Okay, well, great, cool. Let's look at the vertical speed. The vertical speed starts off. No, you don't have to copy this, don't worry. The vertical speed starts off at, where is it? Come on. At 60. Then it goes down 60, 50, 40, 30, 12, 10, 0. And then it starts to go negative. So the speed slows down as it goes up. Watch this arrow. And it gets bigger and bigger and bigger as the longer it falls for. So that speed changes. Unlike the other one, unlike this one, where the speed gets faster and faster and faster downwards, first this has to slow down going upwards. Then it has to speed up going downwards. It's actually one also last critical part, which is this point right here. That's where, well, to be honest with you, it's not that point. It's actually this point right. It's gone. That's when there is no upward speed. And that one point is going to be really useful to us because that helps us split this into two sections, the up part and the down part. But we're going to explore that a little bit later. But again, the main idea that I guess I want to get through to you guys is that this one changes. This one is the same. The horizontal speed is always the same, whereas the vertical one changes because of gravity. That's all I really want you to understand from both of these two slides. Now, this is just a quick little slide just to write it down. Vx is going to be what we use to represent our horizontal velocity. So that's our speed horizontally, whereas Vy is what we're going to use to represent our vertical velocity. The same, of course, would be true, of course, for S, X, and S, Y. Sorry, your distance along X and your distance along Y. So and then we'll talk about those later on. But this is just going to be just a quick little point here. This is another picture as well of projectile motion. This is water in projectile motion, and it's still making a parabola. Initially the water spurts out. It's going very, very quickly upwards. And then at the end, it's going very, very quickly downwards. And here, it's actually not moving up or down at all. It has a zero speed upwards. Yeah, just writing down V of X is horizontal velocity. And if you don't remember what horizontal means, you know that does sometimes happen. It's this way, whereas Vy is our vertical velocity, it's up and down. Okay. Next up is going to be the, we're going to start looking at it. We've talked about it. Let's start getting deep into the maths. What I'm going to do is I'm going to give you guys this here. Now, what I'm going to ask you guys to do is I'm going to ask you guys to copy down this table. Now, if you're using a computer program, that should be quite quick. If you are not, if you're doing this into your books, then you just need to take some time and get it down into your books. It doesn't have to be neat. I don't expect you guys to be getting rulers down, especially because I can't see your books at the moment. So all I want you to do is just get this table into your books, and then we're going to talk about it. We're going to look at two things. We're going to look at the displacement, and we're going to look at the velocity. I'm going to give you guys a while to copy this down because I know that students usually take a little bit. So I'm actually going to give you guys 2 minutes to copy this down and the text as well. The picture down the bottom left, you don't need to copy that picture down. I'll cross that out so you don't accidentally do it. But I do want you to copy down the first little bit. So I'll give you guys 2 minutes to copy that down. And then what we'll do is we'll start working on this type of problem. If you've just joined in and you're sitting here thinking, why am I on a Zoom that's completely silent? It's because you haven't been listening. I would like you to copy down this table. We're about to start cracking into it in about 20 seconds because I'm timing. I'm timing 2 minutes here because I'm itching to start teaching. But you know, like I want to give you guys a chance to copy this down. Okay. All right, so here we go. So let's read this question and then we're going to make a start. So a man drops an apple off the top of a 100-meter tall building. Okay, that's going to be important later on. It's accelerating towards the ground at 10 meters per second. Okay, we can do this. So let's write that down. We're going to write down x. Well, that means at 0 seconds before he drops the ball or apple, whatever it is, off the building, how high is it above the ground? It's 100 meters up. Okay, I don't need that m. I can just write 100. And how fast is it going when he drops it? Well, and when he lets go of it, it's going to be traveling at 0 meters per second at the very, very start. Do you guys agree with that? Does that make sense? I need a yes from chat, please, if that's all right. Cool. Yep. All right. So now we're going to start ramping this up. What happens after 1 second? How far is this going to be above the ground after 1 second? Well, how do we calculate that? We've got a initial speed of, or in this case, we've got an initial speed of 0. We've got a displacement s of 100. Well, we don't know what the new displacement is, so we can't even write that down. We know we've got an initial speed of 100. We know a is going to be -10. We know that t equals 1 second. We can use those to figure out what x is. We can use those to figure out what our new displacement is. We're going to use the formula x equals ut plus half at squared. Whoops. Sorry, my old answers are gone. So we're going to write that down. We're going to write 100 and 0. So let's calculate, and I'm going to do this in green for our very first one. We're going to calculate this for 1 second. We're going to go, well, x equals, in this case, our initial speed is 0. So we're going to go 0 times 1 plus a half times 10 times 1 squared. That means we're going to end up with, well, actually, by the way, that a is downwards, so that should be times -10. So that's going to be 0 times 1 is going to be 0. A half times -10 is going to be -5. Times 1 squared is going to be 1. It's going to be -5 meters. The -5 meters, that means that this is now going to be 95 meters above the ground. So now this is 95 meters above the ground. We can now use this to figure out some other things. So let's work out the velocity. To work out the velocity, we're going to use this formula here, v equals u plus at. Now, the reason we use these two is because these are our kinematic laws. We've never seen these formulas before. V is equal to, so therefore our v equals u plus at. U is 0 plus take away 10 times 1 equals -10 meters per second. So that means our new speed is -10. Does that make sense to people how I got those two measurements, how I got the velocity and I got the displacement? Can I get a yes in chat if that makes sense to you? If you didn't get that and you need me to re-explain it, let me know. Chat says, yeah, that makes sense. Okay, cool. So I'm going to do another one. We're going to do now, I'm going to do this in, can I do this in yellow? Not really. I'm going to do this in, they will be provided. Someone said, do we have to remember all these formulas for the test? Like, no, don't worry. You'll be allowed to make a one-sided cheat sheet, is usually what I say, one-sided revision sheet. So that's what I'll let you guys use. So let's do the second one here. So let's look at 2. How do we do for 2? Well, we're going to use the same measurements. We're going to do the same measurements. We're going to do that here. So we're going to say x equals ut plus half a t squared. U in this case is still 0. 0 times, but t in this case is 2 plus a half times -10 times 2 squared. Okay, so that's going to be x is going to be 0 times 2 is going to be 0. A half times -10 is going to be -5 times 2 squared, which is going to be -5 times 4, or -20. Now that's going to be meters. So that means that we write down 100, take away 20 is going to be 80. Now some people might say, why did I take away 20 from the 100 and not from the 95? The reason I took away 20 from the 100 and not the 95 is because we are measuring 2 seconds. We're measuring this 2-second gap, okay? And that's why I'm measuring it that way. That's not to say that you couldn't do this using the 1 second if you wanted to. I can show you that. It's a little bit more complicated, but it still would work the same way. X equals ut minus plus a half at squared. But this time, you'd say t equals 1, which is fine, plus a half times negative 10. But your u would have to be negative 10 because you're already traveling at negative 10 meters per second. Doing this gives you negative 10 take away 5, which becomes negative 15. And if you subtract 15 from 95, you get 80. But you shouldn't really worry about doing it this way. The only reason why I put that there is to prove to you, hey, you can do it. Let's do the velocity now. So the velocity, v equals u plus at equals 0 plus, we take our initial speed to be 0. We take our final speed to be negative 10 times 2, which is going to be negative 20. Negative 20 meters per second. That's how we can do 2 of them. I want you guys, I'm going to give you guys 3 minutes, but I want you guys to do 3, 4, and 5 for me. So I want you guys to work out the displacement after 3 seconds, the displacement after 4 seconds, the displacement after 5 seconds. I want you to use these formulas. And I've given you guys all the tools. So the next one that you'll have to do is pretty much do this orange one, except instead of 2, you substitute a 3. So I'm going to give you guys, yeah. I'm going to give you guys what? Say about I tried to do a rainbow and I failed miserably because it started with green. I started with blue and I think I made a mistake, but it doesn't matter. Rainbows are not important. What I'd like you guys to do now is try these last 3. I'm going to give you guys, try these last 6 boxes. I'm going to give you guys 3 minutes to do it. So you guys got plenty of time. You've got till 12:20 to do it. And then what we'll do is I'm going to ask you guys to put your answers in chat. But I won't get you guys to do that yet. I'll get you to do that after you calculated them. So calculate those last few. You guys may find that the 5-second one produces some interesting answers, but we'll talk about that in a second. Talk about that in 94 seconds to be precise. Okay. So can I get someone in chat to tell me after 3 seconds, I'm going to change my pen to red. After 3 seconds, put this in chat, someone. And I'd like to get a different, these last 6 boxes, I'd like a different person to answer each time. I would really appreciate that. So they can show me whether or not you guys understand this. After 3 seconds, how far above the ground is our apple? Can someone tell me how far above the ground is our apple after 3 seconds? Now 80 meters is how far it is about after 2 seconds. I want to know after 3 seconds. 55, thank you. After 3 seconds is 55 meters. Thank you, Eric. Can someone tell me what speed is it going? This is actually an easier answer to work out. What speed is it going? Don't stress, Eric. That's all right. Elaine, do you know what speed it's going? It can be anyone, by the way, if anyone wants to help you guys out. Elaine actually gave me an answer. She said it properly. That's okay. It's -30. Beautiful. So that's correct. And the reason, can anyone, by the way, while we're going through this, can anyone see what the pattern is in the, can anyone see, pay attention to tell me if you can find out what the pattern is in the speeds. Okay, so then the next one is, what's the displacement after 4 seconds? Now, who can I ask this to? Let's have a look. Can someone either answer me, or else I'm just going to pick someone at random? Well, maybe Everest. You've been helping us out a fair bit. Everest, what is the displacement after 4 seconds? Or anyone, by the way, if you guys want to help him out. You guys are sick of sitting here waiting. I don't know, sorry. Okay, what about Najila? Do you know what the displacement is after 4 seconds? Come on, please. 20? 20. Yep, 20, I believe, is the correct answer. It is 20. If you want to know how to calculate 20, Everest, you were, and both Elaine Lords, is that, on what's the speed? How fast is it falling? -40. Nice. Now this one, by the way, Everest, you said you didn't know how to do it, so I don't know, sir. Sorry, so let me show you, because if you don't know how to do it, I'll quickly pump out the equation down the bottom here. It would be x equals ut plus half at squared. Now u is 0, so that's going to cancel out because we're just going to take u as being 0. We're going to go, therefore, x equals half times -10 times t, in this case is 4 squared, which is going to be a half times, so this is going to be half times -10 is going to be -5 times 16, which is going to be -80. So that's how you get 20. 100 take away 20 is 80. So the last one is really weird. We've got -40. Now, some of you should be like saying, wait a second, and I'm going to write down the answers here. Sorry, this is -40, whoopsies. The speed, yeah, thank you for that, Everest. Can I get someone to tell me, does anyone know what the 5-second one is? It should be weird. You should have gotten a weird answer. I got -25. Good. That's roughly what you should expect. -25. Now, you might think to yourself, that doesn't make sense. And you're right, that doesn't make sense. That implies now that our object is going below the surface of the ground. And that's because, yeah, that's what has happened here. If you were to assume this, it would have fallen 125 meters. So therefore, you wouldn't, at 5 seconds, your displacement probably isn't -25. It's probably actually 0. But because it's not going to fall it's not going to fall further than the ground level. So what that does is actually gives you an interesting question here. what we're going to do is we're actually going to say, well, how long does it take to hit the ground? How do you work that out? Well, you can actually work that out.
Don't you just do, wait,
Go.
so don't you just plug in x as negative 100?
Exactly. If you take this formula here, you put in 100 equals ut plus half at squared. We know that ut is 0 times, is going to be 100 equals 0 times t plus a half times negative 10 times t squared, because, yep, 100 equals a half times negative 10 is going to be negative 5t squared, which means you've got, when you divide both, we're just going to deal with, yeah, oh, you'll see why. I'm going to cheat in a second, but you'll see why. You'll get 100 divided by 5 is going to be 2 equals t squared. But yeah, if you got what am I doing? 20. Sorry, pardon me. 100 divided by 5 is 20 equals t squared. Now, I've had to get rid of the negative here because the reason is you've got to ask, it's actually going to drop 100 meters. That's why it should actually be negative divided by negative. And the reason that you're saying it's dropping is because ultimately the displacement's in the same direction as acceleration, but I'm not going to dwell on that. So that means that t is actually the square root of 20, which means that if you take the square root of 20, you should get square root of 20, which is what, roughly 4.47. So we're going to go with 4.5. So roughly right around here is where it hits the ground, between the 4th and the 5th second. We've actually worked that out by taking the formula that we keep using and saying, well, I'm going to plug the answer in. Tell me, what was the question? How long will it take to get there? Now, some other points that I want to make out about this graph before we jump to the next idea, and I'm probably not going to fill you guys with too many more ideas, but before we get into the next ideas, I want you guys to look at the two columns. Can someone tell me what is the column? What is the pattern in the column with velocity? What is that? What is the pattern going on there? Can someone write in chat or say out loud what's going on in that velocity column? Someone speaking, that's fine. Tell us what's going on in the velocity column. Unfortunately, it's a bit broken up. So maybe you might want to write it in chat instead so that we can work on it. What is the pattern in the velocity column? It's going up by 10 every second. And that is correct. It is going up by 10 every second. The reason it's going up by 10 every second is because we've got an acceleration of 10 meters per second squared. So every second, the velocity increases by 10. It gets faster and faster and faster. And that means that you can easily go, well, after another second, it would be going 60 meters per second. But what does that mean for our displacement? Well, I'll tell you what it means because I'm afraid that it would take me forever to get you guys to answer the question. But the displacement doesn't go down by a stable amount. First, it goes down by 15, right? That, okay, sure. Then the next second, because it's traveling faster, no, first it goes down by 5. Then it goes down by 15. Then it goes down by 25. Then it goes down by 35. It's actually going, the distance that it's traveling is getting more and more and more, and that's because it's going faster and faster and faster. So that's what we want. I want you guys to take away from that is that, yeah. So these two equations here, let me just try and clear some of this up. I will put these slides up. If you need me more time to copy some of these down, you need to let me know. But these two equations here are just our kinematic laws. This happens to be the third kinematic law, and this happens to be the first kinematic law. But these are the two laws that will help us a lot with solving problems with these types of questions. We always know that acceleration is -10. That makes life really easy for us to calculate. And we know that if acceleration is always -10, we can then use that to work out velocities and so on and so forth. So what else can we do here? I wanted to start off by showing you this formula here. This is the formula we just had on this slide. So vertical displacement is based off this formula. Now, the motion is not linear. And the reason this motion is not linear is because this equation is not a linear equation. Look at it. It has t squared. This is actually a parabolic equation or a quadratic equation because it traces out a parabola. And that's exactly what we need to understand when we plot this kind of graph, that it's not just as simple as, oh, you know, it's not as simple, it's going in a straight line. Now we're dealing with a parabola. It goes up, and then at a certain point, the displacement, the distance away from the object, goes down again. It doesn't go like, if you remember our velocity time graphs, in this case, this is a displacement time graph. Our displacement time graph is not a straight line like we were used to doing. This displacement time graph is a curved line. So yeah, I'm going to give you guys a second to copy this down, and then we're going to move on to maybe a couple more slides. We'll see how far we can get, and then that will be the end. So I want to quickly, we'd like to do one more question about this, but yeah, copy this down first. I'd also like you to draw a little picture, if that's okay. It doesn't have to be as detailed as the picture that's down there. All it needs to have is just a displacement time and a curve like this. Okay, so let's now, sorry about that. Let's now move on to the next sort of idea with this. So probably what we've dealt with probably the most simplest case, which is dropping something in gravity and looking at how it speeds up over time. But really, projectile motion deals with more than just that. Projectile motion deals with moving an object moving in more than one dimension. So we're going to try and explore this, and we're going to do this by looking at. We're going to look at this question here. We're going to do this one here. Okay, we're going to do this here, which is not actually a proper question, but we're going to explore it like it is. A football is kicked from the ground. It has a vertical velocity of 20 meters per second, and it has a horizontal velocity of 20 meters per second. I want you to jot down those first key parts, and then we're going to try and tackle this. This isn't actually a question here, but we're going to try and find some key facts. I'm going to write down our two equations that we're going to be using. X equals ut plus half a t squared. We're also going to use v equals u plus at. We may also just use the displacement is equal to the, well, actually, I'm just going to leave that out. So they're going to be our two formulas that we're really going to use for this whole type of question here. Well, the next thing I'd like you to do is, can I get a suggestion while you're copying this down in chat? What do you think, what kind of facts do you think we could calculate for this question? What facts would, if I'm kicking a football, what facts do you think I might want to find out? It's actually a very reflexive question. What was that? What facts do you think we're going to try and figure out for this question? How far / how high? Those are probably the main ones. We're going to look at how high it goes. We're going to look at how far it goes. And there's one more question that we can actually, it's actually probably one of the key questions that we're going to put in the middle here. What do you think it is? How far?
How long does it take?
What?
How long does it take?
How long? We're going to answer all of these three questions. How high does the ball go? How long does it take for the ball to travel? And how far does it go? And we actually need to answer them roughly in this order. You can switch the order of these two, but you can't answer this one without some of the others. So let's start to explore this, okay? We're going to look at how do we explore this type of question? Well, what we would do is we're going to look at how high does the ball go. Well, how high does the ball go? Well, we can't actually, and this is the trick here, you can't work out how high the ball goes without knowing, well, how long does it take to get there? And the trick to doing that is this. In fact, what I usually call this is I'm going to call this time. And we're going to do different colors as I go through this. I'm going to start here in maroon. We're going to go time to reach peak. Oh, you might want to call this peak time. It doesn't matter, but yeah, we want to know how long does it take for the ball to get from here to here. What is the time that takes? So how we calculate that is we say, well, at the peak, right? At the peak, our velocity upwards equals 0. Our velocity upwards equals 0. And that's actually going to be pretty, I want you to think about that. I would really like you to understand that. When you throw a ball up, how do you know that it's gotten to the top of its arc? You know that it's gotten to the top of its arc when it's not moving upwards anymore. You know that it's got to the top of the arc because it starts to fall downwards. So that means your vertical velocity is 0. I know that it's just writing down a v equals 0. That's cool. A lot of you guys could do that. But I actually also want you to understand, what does that mean? Our initial velocity upwards, well, that's 20. It's 20 meters per second up. And now we know our acceleration, well, that's -10. That's downward. So now we have u, v, and a. We can use our formula v equals u plus at, which means that I'm going to rearrange this, but I'm going to do this. If you would have to do this on your own, v minus u divided by a. That means that we're going to end up with v, which is 0 minus 20 divided by -10, which is going to be -20 divided by -10, which means that our final answer is 2 seconds. It takes 2 seconds for our ball to go from the bottom to the very, very top. T equals 2. I'm actually going to write T half so that we know. Actually, you know what? No, not T half. We'll call it T peak, TP. So how long does it take to get to the peak? Now I've got an interesting point here. Actually, we can actually answer one of these questions straight away. How long does it take before it gets to the ground? If it takes 2 seconds to get to the peak, how long do you guys think it's going to take to get to the
4
ground?
seconds.
How long?
4 seconds, sir.
How did you get that?
I looked at the graph, and then if you go halfway is 2, and then you go times 2 halves is 1 whole. So
Beautiful. 100%. So the time total is equal to 2 times, in this case, the time to the peak, which is going to equal, I'm going to write T total equals 2 times 2, which is 4 seconds. Now I do want to point one thing out here. And this is going to be something, this is something for those uber nerds here. If there is anyone out there that's like, oh my God, this is really, if there's someone here that's an uber nerd that's like, I'm going to get 100% on the test, just quickly pointing out, this is going to be the answer for everyone, but if there's anyone here that's super nerdy, this doesn't always work. This trick that we've done here, works because it's symmetrical. But if our graph wasn't symmetrical, if we were on top of a cliff and we were throwing something down, you couldn't use this. You wouldn't be able to say, oh, I'm just going to calculate the time for the first half and multiply it by 2, because it's going to take you a very, very short time to get to the top and a very, very long time to fall down after the cliff. So you can't always use this cheat. But for this situation, hold on.
It's like they're walking around water.
For this situation, you can use this symmetrical feature. And for those of you that are now freaking out thinking, oh my God, have I got to learn something new? No. For engineering maths, which this is already a very difficult concept for, but I'm only going to expect you guys to be able to approximate it for symmetrical. If you want to know how you would do it, is you would need to know this next fact. We now need to know, let's work out how high does the ball go? Well, we now know, we want to calculate x. And we want to know, and we now know for this x equals ut plus half at squared, we now know that the time it takes is 2 seconds. T equals 2. U equals, and the upward speed is 20 meters per second. A equals -10. So let's put those numbers in. X equals 20 times 2 plus a half times -10 times 2 times 2 squared. And for those of you that want to, yes, that's going to work. So I was a bit like, oh my God, I think I've broken it, but no. For those of you guys that want to know as well, for the record, the reason that the initial speed is positive, but the acceleration is negative, is because they're in opposite directions. That's why that negative played a bit of an issue with us with the falling apple off the building. Plugging the numbers in, 40 plus a half times -10 is going to be -5 times 2 squared is going to be 4. It's going to be 40, take away, -5 times 4 is going to be -20 equals 20 meters. So this ball is going to go 20 meters into the air, 20 meters up. So now, but here's the thing, right? And this is one of the things I want to point out. We wouldn't have been able to figure this out without knowing how long it took to get to that peak height. So that's going to be a really important concept. We actually really need this time to reach peak as our very first thing that we figure out for these types of questions. The last thing that I'm going to draw our attention to is the horizontal, how far does it go to the right? So let's do this in orange. Yeah. How far does it travel? And this is, you might think, sir, there's not enough space for you to answer it. And the reason is that, don't worry, there is. We know that we can use any formula you want, but I'm just going to use displacement equals velocity multiplied by time. The horizontal velocity is 20 meters per second. And the time that it spends in the air is 4 seconds. So 20 times 4 means that it will travel 80 meters. And that is our final thing. Now, you can also use this to say after 2 seconds, it will have traveled 40 meters to the right. So at this point here, it's 40 meters to the right and 20 meters in the air. So you could use that. That could be an important information if you wanted to try and figure out how high an object is going to go, whether it's going to clear a certain thing. That would be a bit of a measurement here. But that's how we can use, and if you guys look, we actually have only used these two formulas. You might say, but so you used a brand new formula here. To be honest with you guys, if you really wanted to get nerdy, this formula here is just this formula at the top. The only difference is that I've said, well, the acceleration is 0, and that's true. Horizontally, it doesn't speed up, it doesn't slow down, it just travels at 20 meters per second the whole time. So if you travel at 20 meters per second for 4 seconds, you will go 80 meters. And that is pretty much all of the types of questions you could get asked with some sort of projectile motion type question like this. Now you could go backwards and you could ask questions and you could say instead, what is the initial velocity needed to make a ball go 30 meters into the air or something like that. But for me, these are the main types of things that we can do. You've got to find out how long it takes to get to the peak. How long does it take in time in total? We've got to work out how high an object goes and how far does it travel. Now, you don't always need to work out how high it goes, but you can't work out how far it goes without knowing the total time. And what I'm going to do, by the way, if I give you guys questions in tests or questions in worksheets, is I'm going to step you through these types of questions. I'm not going to go, right, go, fine, tell me how far it goes. I might say, how long does it take to reach the peak? How long does it take in total? How far does it go? So then I can lead you through step 1, step 2, step 3. I'm going to lead you through this as a path rather than just go, yeah, calculate this straight away. Now, I know this is probably a bit confusing and daunting, but I'm going to ask anyway. Are there any questions? Are there any points on here that you guys are like, okay, can you re-explain? I've done it in different colors. So if you guys say, well, sir, can you re-explain that purple bit? Or can you re-explain the green bit? Or how in the orange bit, how did you do this? So I'm opening it now. Are there any questions? Otherwise, I'm going to do maybe start. I'm going to do one more small question, and then we're going to wrap it up for the day. Are there any questions? Do we always have those two formulas for projectile motion, or is it just the scenario? You should you would always use those two formulas. Those two formulas at the top, they're your best friends in projectile motion. Now, I guess you could ask the question, do you ever have to use any of the other formulas? And it's like, it's usually rare, but yeah, you know, you could use some of the other formulas. You could use you could use you could actually skip this. You can actually work out how high it goes. If you go use this formula, x equals u plus v divided by 2 multiplied by t. You could use that formula to work out how high something's gone, but you still need to know the time taken. So it's like, we'll just use this formula here, even though, yeah. So you could use that formula there. You could use, you probably wouldn't use x equals vt minus half at squared, because you could use that, but it would be a bit more complicated. But yeah, you probably wouldn't use that one very often. And I'm trying to think of yeah, and v squared equals u squared plus, yeah, you're gonna mostly be using that one. And yeah, so those two formulas, they're the ones that I'm gonna really put up a lot so that we can use them. Are there any other questions? Any queries? That was a private question, by the way. If you're wondering why I just started randomly talking, obviously that person didn't want everyone to know that they were confused, but that's fine. And that's what I'm encouraging you guys to do. It's actually really rare that you guys can actually, and I want you guys, that you guys can actually ask questions without everyone seeing and saying, oh my God, this person's an idiot, you know, they don't know how to do this. You can ask it, and I won't victimize you. I won't say, oh my God, like, you know, look at this, Lucille is an idiot. They've said this. I can't even say Lucille asked this dumb question, because I choose just to completely keep you guys anonymous. It's interesting though, because even though you guys are anonymous, you guys can send me private messages. You guys don't always do that. And I reckon the reason that you don't always do that is because you've been trained after so many years, don't ask dumb questions, because, you know, you don't want to look stupid, but you know, that's the best way to learn. The amount of dumb questions I ask, people think I'm an idiot because I ask so many questions. That's the thing, they don't realize, like, I've got a master's degree. I actually know a lot of stuff. I ask a lot of questions because I want to learn. Let's do one last question. We've got about 10 minutes left. If your brain is melting slightly, don't worry. We're not going to go through. We've got like a lot. We won't go through all. I'm trying to figure out. Okay. let's skip this one. Let's do these two because I reckon we can do these two really quick. Don't draw the picture. We've got our two formulas. No, we've got one of our formulas here. X equals ut plus half at squared. And then with the other one that we've been using, v equals u plus at. Let's do these two. Let's do these two real quick questions here. The rocket's fired upwards at 30 meters per second. When will that rocket hit the ground? Okay. So what we're looking for is we want to know, firstly, we need to know how long does it take to get to the peak? We want to know how long does it take to get to the peak height. And once we know how long it takes to get to that peak height, we can then work out how long does it take in total. So how do we work out how long it takes to get to that peak height? You guys remember from the last one, we need to do this. We need to know that our initial speed upwards, well, that is a positive 30. We know that our acceleration downwards is a negative 10 because we always fall at negative 10 meters per second. That means that we just need to work out t. We don't know anything else, but we do know our final velocity. When we reach the peak of our height, we are going to be traveling at 0 meters per second upwards. Okay, that's how fast we're going to be moving upwards. V equals 0. So we're going to use this formula right here. V equals U plus AT. In this case, V equals 0 equals U, which is 30 plus negative 10t. Negative 30 equals 10t. Negative 10t. T equals 3. If t equals 3, then therefore our t total is going to be 2 times our t peak, which is going to be 2 times 3. It's going to be 6 seconds. It's going to take us 6 seconds. And I didn't even need to use the other formula. I just used the first formula. I just said, well, that's how long it's going to take. Okay, I'm going to give you guys a second. If you're copying me down or you're following along, I didn't even give you guys any time whatsoever to write down this question. So what I'm going to do is I'm going to give you guys about a minute to do that, maybe less, maybe about, yeah, I'll give you a minute from here, and then we'll do that bottom question, and then we'll call it a day for this heavy projectile motion question lesson. If there's anything in this lesson you're like, I don't understand, you need to email me ASAP, okay? Okay, oh, there's a question. Oh, that's good. It's a private question, so the person doesn't want to know. How did I get negative 10 as my acceleration? I got lost. That's okay. Negative 10 at your acceleration, and this is one that I can say, is always equal to negative 10. Okay, so your acceleration in projectile motion questions is always going to be negative 10. You don't need to change it. You don't need to look it up. It's just always going to be negative 10. It's one of the only things that I can pretty much say, always negative 10. There are, of course, in year 11, I actually changed the rules a bit. I tell you, to be honest with you, it's actually not negative 10. It's actually negative 9.8. But for year 10 students, we're going to keep this simple. Your acceleration caused by gravity is negative 10. Any other questions? All right, last question of the day. Let's do this. Another rocket is launched upwards at 40 meters per second. When will that rocket reach 60 meters up? Ooh, a different question. So this one is not actually a question of, this is asking when will it reach 60 meters up? So we're asking when will our displacement be 60? Okay, when will our displacement be 60? Well, we know that it's being launched at 40 meters per second. U equals 40. This is a different type of question. Someone's already got an answer, but we'll see if we can prove it. We've got A, which is -10, and T, we want to know how long it takes. When will that rocket, when? So T is our unknown. We've got X, U, A, and T. That means we're going to use this top one. Again, normally this is the same type of question that you could get in a this is the same type of question you could get in a kinematics question. I could have actually given you guys this 2 weeks ago in kinematics, and you would still be expected to do it. The only new flavor that I've given you in these types of questions is I haven't told you the acceleration by gravity. But now you know the acceleration by gravity is always -10 on it. So X equals UT plus half AT squared. Let's solve it. Now, to solve this one here, we're going to go, X is going to be 60. Oh, this is going to be bad. I've made a mistake here. We may have to stop this question early. X equals 60 equals 40t plus, and then that's going to be negative. So we're going to have negative minus a half times 10 times, and the reason it's negative is because of that, minus times t squared. This is actually kind of bad, ladies and gentlemen, because it's going to be minus 5t squared. And ladies and gents, unfortunately for this particular question, I actually need to stop doing this question here. And the reason that I need to stop doing this question here is because you'll see that I've changed this question because I thought I'll give you guys a bit of a different question. But unfortunately, what I've done is this is actually a this is turned into a higher level maths question that I haven't actually prepared you guys to be able to do. I can solve this type of question, but yeah, the rest of the solve of this question would be not expected of you guys to be able to do. I would not expect you guys to be able to solve this question, even though it looks like a type of question you could solve. I don't think you could solve this question because, yeah, it just so happens that it doesn't work. What I'm going to do now is I'm going to say, ladies and gents, what I'm going to do now is this. Ladies and gents, I'm going to do two things really quickly. First thing I'm going to do is, ladies and gents, thank you for coming today and learning. If you've got any questions, please send me an email, and I will gladly go through them. Through some stuff.
Sir.
Hold on, don't worry, Oliver. Just wait. Hear me out for a second. Hear me out. And if you have any questions, send me an email. We're going to continue with this stuff tomorrow. Now, what I'm going to do is this. All the people that want to leave, by all means, leave. What I'm going to do now is I'm going to finish this question, but I'm going to use stuff from advanced maths. You are not expected to be able to do this. This is not going to be on the test, but I will show you how to do it. Oliver, does that answer your question?
Oh, yeah, I was going to tell you how to do it.
Yeah, don't worry. I know how to do it. I want to give people that are like, I don't really care. I don't need to learn this. I'm leaving. But I'm going to do it now anyway. What we're going to do is we're going to wrap this up. How would I wrap this up? I'm going to move 60 to the other side. That gives me 0 equals -5t squared plus 40t minus 60. Going to divide everything. So that's now equal to 0. We're going to divide everything by
-5.
-5, because that's going to make that equal to just t squared. That's going to give us 0 equals t squared. We're going to have, that's going to
-8.
-8t, and then that's going to become plus 12.
12.
So then what we would do is, for those of you that know how to deal with the null factor law, we would turn this into a null factor law. I would look for a number that multiplies to 12 and adds to 8. That's probably going to be -2 times -6, because that's going to add to -8, but it's going to multiply positive 12. So it's going to become t minus 2, t minus 6. Therefore, t equals 2, t equals 6. When will the rocket reach 60 meters? In 2 seconds. Now, some of you guys might be looking at that and saying, but sir, there are 2 answers. How do you know which one's right? They're both technically correct. What's going to happen is, after 2 seconds, which is here, we're going to reach our 60-meter mark, and then it's going to keep going up. But then after it's gone up, it's going to start falling back down, and it's going to go past that 60-meter checkpoint again at 6 seconds, and then it's going to keep falling down until it eventually hits the ground. You can also use this, by the way, to figure out, well, when is it going to reach its peak? Its peak is going to be halfway between these 2 points, so therefore it's going to reach the peak at 4 seconds. But that's just another thing you could do. So yes, ladies and gents, it is possible to solve this type of question, but I would not expect you guys to be able to do that as part of engineering maths. But I know some of you guys, I've got 14 people still here. I know some of you guys are a little bit nerdy and maybe would be interested, but that's how you would do this type of question. I'm gonna have to remove this for next year, but you know, I'm not gonna ask you to do that, but hopefully it gives you a better understanding of, hey, that stuff that we learned about quadratics, guess what? It actually has engineering potential. We do care about these types of things, because if you don't know how an object is going to behave as it moves through the air, you are going to be in trouble. And so that's why it's important to have these quadratics part of our understanding. Ladies and gents, now I'm officially closing the class. Thank you so much for listening, and I will see you tomorrow. If you've got any additional questions, you can stay on the line and ask them now. I will put these up online as soon as I can. See you later, guys.